Hi, good morning, everyone. I'm Leah Gleason from Headwaters Science Institute, and we are very pleased to have Dr. Katie Wilson here with us. Hi, Katie, how are you?
Hi, Leah. Great, thank you. Happy to be here.
Thank you so much. We are so excited. Dr. Katie Wilson works at the National Oceanic and Atmospheric Administration in the National Severe Storms Laboratory. And she loves studying weather and people. She has found a career path that incorporates research in meteorology, human factors, and related social science fields. So she's combined all these fields together to study something really, really exciting. And she's going to talk a little bit about her work in forecaster decision making today. And she spends her time exploring questions that relate to the intersection of research and operations. So a lot of interesting interdisciplinary research that she's going to tell us about today. So Katie, we're so excited to have you.
Great, I'm so excited to be here.
So before we turn it over to you, I just want to thank our sponsor, the Tahoe Mountain Resorts Foundation. This is a local organization to our area in the Tahoe Truckee area. They give grants and scholarships throughout the community, and they've been a long-time supporter of Headwaters. So we're really happy that they have supported online learning. Sponsors like this help us keep online learning free. So if you are watching and you own a business that would like to support our programs like this, or a Lunch with a Scientist day, please reach out to us. And so without further ado, Katie, I'm going to turn it over to you.
Okay, wonderful. Thank you, Leah. Okay. Well, thank you so much for joining me today. It's an absolute pleasure to spend this lunch with you, sharing the science that I do. Today, I'm going to be talking about the science that happens between research and operational meteorologists. Now, there are many types of research avenues in meteorology. Meteorology itself is an atmospheric science. We study the atmosphere with a focus on weather forecasting. And I know that you've heard from a couple of my colleagues already earlier during this series. You heard from Dr. Elizabeth Smith, and she talked about her research where she goes out into the field and she actually chases thunderstorms. And when she finds them, she takes observations so that she can learn about what it is that makes thunderstorms do the things that they do. And then Dr. Kim Clocko-McLean talked about tornado epidemiology. And so she's very interested in when tornadoes impact communities, how do the people living in those communities respond to the threat? So what is the decision making behind their protective action, and how can we help limit the number of fatalities that occur during these events? And today I'm talking about the intersection of research and operations. So this is a little bit different. So today, when I'm talking about research, what do I mean? When I talk about research, I'm talking about the work that aims to advance and develop the scientific knowledge and the technology beyond what our current understanding and capabilities are. And then for operations, we often think of it in terms of applying the science to meet a real world need. And in my research, a lot of that is with respect to National Weather Service forecasters and the activities that they are responsible for. And so why do we care about the intersection between research and operations? Well, the reason is because we want to bring the maximum benefit to the operational mission. And for the National Weather Service, that is to protect life and property. And we want to make sure that the advancements and developments that we make on the research side are understood by the users, they are useful to the users, and they have a positive impact on the operational process that already exists. So we don't want to do any harm, we just want to do good. Okay, so you might ask, well, how do you do this type of research? And by the end of this presentation, I hope that you have a better idea of how we as scientists are addressing this research need. So one way that we address the research need is through something called the Noaa Hazardous Weather Testbed. Again, Noaa is the National Oceanic Atmospheric Administration. It's the agency that we're under. And the Hazardous Weather Testbed is a really special place. It's a venue located in the National Weather Center here in Norman, Oklahoma. And it's a place where we bring together researchers and operational folks, as well as other end users, to find out how they might use the things that we are producing. And so the top picture that you're seeing is showing a snapshot of an experiment that's ongoing. So you've got 2 forecasters working at some stations there. And then the bottom picture is a panoramic picture of the hazardous weather testbed room. And so what you see in the middle is you have the hazardous weather testbed, and you've got windows either side. So that's the place where we do a lot of our experiments. Now, what's really cool about this venue is either side we have operational offices. So on the left, we have the Norman Local Weather Forecast Office. There are 122 different offices around the country. That's a lot, but they're each responsible for a county warning area. So that's a small segment of the United States, and they issue the local forecasts and warnings. On the right of us, we have the Storm Prediction Center. So that's a little bit different because that's a national center, and they look at the severe thunderstorm threat across the entire country, and they issue products from days before thunderstorms occur to the day of. So for example, you might be familiar with the tornado or severe thunderstorm watch products that come out of that office. What's really cool about having these folks either side of the hazardous weather testbed is it promotes this operational environment that oftentimes we're trying to simulate in our experiments. And it also provides an opportunity for those operational meteorologists to come and interact with us and learn about what we're doing. So there's a lot of great work that takes place, a lot of different scientists doing different kinds of work. But to give you a taste of what this work looks like, today I want to share with you 2 different projects that I have worked on and am working on at the moment. That's phased array radar and weather model guidance. And I just want to give you a feel for how we go about conducting some of these interdisciplinary studies and how we go about tackling some of our research questions. So I'm going to start first with the phased array radar project that I worked on. So just a little bit of background in case you aren't too familiar with weather radar. The top left picture is showing a weather radar. It kind of looks like a golf ball on a big metal stand, but the golf ball looking thing is a radar dome. And within that, we have the actual radar instrument itself. It's a big dish. And this instrument is able to look into the atmosphere and provide us a picture of what's going on. Next to that image, you see the picture is the United States with lots of circles all over it. That's showing the 158 different weather radars and their locations and their coverage. So we see some gaps in the Western United States, but otherwise we're pretty well covered in terms of weather surveillance. And this instrument is incredibly important to weather forecasters. It gives them a real-time picture of what's happening outside. And what happens is the radar emits an energy beam out into the atmosphere. That beam goes out, and if it hits a target, that target could be rainfall, it could be snow, it could be hail, it could be a bird. It might even be the top of a wind farm. If it hits something, the energy is scattered everywhere. And a small piece of that energy is returned back to the radar. The radar listens and it records the signal that comes back. Now we're able to get a lot of information from that energy. And through lots of very complicated magical processing, we're able to look at the radar data through different products. 2 products that are really important to forecasters is reflectivity and velocity. Reflectivity can tell us something about the strength and the structure of a storm. And so you'll see higher values of reflectivity if, for example, there's very heavy rain or if it's going to hail. And then we have velocity. So this is a picture that is full of greens and reds. The greens represent inbound motion, so motion towards the radar, and the red represents outbound velocity, so that's motion away from the radar. And what this does is it can tell us about the way in which a storm's moving. And so in this picture, you're seeing these greens and reds very close to one another. So we actually have a rotation couplet, and we see this kind of signal when tornadoes are occurring. Okay, so this is weather radar, super important to weather forecasters. If you have a thunderstorm in your area, you can guarantee that a forecaster is looking at the radar data and analyzing the storm trends. But what is the research problem? So here's the problem that we were trying to tackle. On the left, you see a picture of the current radar system that weather forecasters use. You can see that there's this big dish-looking thing. And the way in which this operates is it turns all the way around. It does 360 degrees, scans the atmosphere, and then it goes up a little bit, and it goes around again, and it keeps doing that, going up in tilts until it has created a full picture of the whole storm. And that takes about 4 to 6 minutes to get a full volume update of the thunderstorm. Now, on the right, you see a picture of a different kind of radar technology. The radar dome is kind of suspended in the air because this is when they were installing it. But you see this flat panel. That's the phased array radar. And it can move a radar beam electronically, which means rather than turning this entire dish, we can instantaneously change where the beam is looking. And this difference in technology means that we can update the radar data every minute. And so with that, forecasters could see radar data at 4 to 6 times the rate that they currently do. So that then brings the research question of how rapidly updating radar data impacts forecasters' warning decision-making processes to the forefront. That's a very important research question to try and answer. And so to do that, we've done a lot of different experiments. And today I'm going to share with you just a few different examples of the type of approaches we've taken to understand the warning decision process with respect to radar data. And so I'm going to talk about the between groups experiment we did, an eye tracking experiment, and focus groups. Okay, so the between groups experiment, this is a way that we can try to really assess what the impact of temporal resolution is on forecasters' performance, so the types of warnings that they're issuing and their workload. And so what we did in this experiment was we invited 30 forecasters from different National Weather Service forecast offices. They came to the Hazardous weather testbed and they participated in this experiment. And so what they did was they worked 9 weather events. We showed them radar data that we have archived from past cases, but what we do is a displaced real-time simulation. So we pretend like this is real time, and we say to the forecasters to go ahead, analyze the radar data, and make the decisions like you would if you were in your forecast office. Now, what we did to assess the temporal resolution impact of the radar data, so how fast it updates, was we had 3 different data conditions. We provided some forecasters with 5-minute updates, so that's similar to the radar technology they use today. We provided other forecasters with 2-minute updates, so that's kind of in the middle of what the current technology and the new technology provide. And then we had the 1-minute update. So that's the full temporal resolution of the new technology. So this is just a quick overview of some of the things we found. So in this table, we're looking at warning performance. When we talk about warnings, I'm talking about, for example, your phone starts buzzing because there's a thunderstorm in your area and you're in a warning. It might be a severe thunderstorm warning or a tornado warning. Now in this table, we looked at different measures. So the top row is showing median warning lead time. And then if we go across the different columns, we've got the slowest updates, the medium updates, and then the full updates. And so what we see is longer warning lead time when forecasters were using the fastest radar update speed. And so that's the phased array radar technology. So what we saw was with this new technology, forecasters would be able to provide you with greater warning lead time, meaning that you would have more time to prepare for when the storm impacts. And then we also looked at warning accuracy. So that's the probability of detection. So that's saying for every severe event that occurred, so wherever hail fell or severe wind gusted or wherever there was a tornado, how many times were forecasters able to provide a warning for that event? And so we saw higher scores with the fastest radar updates. So that means that forecasters were able to better detect these events when they saw the full radar data. And then we looked at false alarm ratio. And so we want to see lower numbers for this measure. This says for every single warning that a forecaster issued, how many times did nothing happen in that warning? So such that the public didn't actually need to take action. And so we see that the score is fairly similar across all 3 data conditions. It went down a little bit for the fastest radar updates, but certainly we didn't see that the fastest radar updates prompted forecasters to issue more false alarm warnings. So that's good. Okay, so overall, it had a positive impact on performance. We also looked at workload. Now, you can imagine if we're suddenly providing somebody with 4 to 6 times the amount of data, and we expect them to be able to analyze those data and make sense of it in the same amount of time, that could be quite a challenge for workload. And so we looked at cognitive workload in particular. So this is the mental effort that you exert to do a task. And this diagram down here is showing the results from the high levels of workload that were reported. So we did see that high levels of workload happened twice as often when forecasters used the fastest 1-minute updates. But if they use the medium speed or the slower speed, so 2-minute or 5-minute updates, then they experience high levels of workload about half the time. And the main reason why the full speed or the fastest radar update groups experience higher workload was, first of all, because of storm characteristics. So for example, they were able to see signatures or trends in storms that would indicate that something was going to happen more easily, but also temporal resolution, being able to take a normal process or practice of how you analyze data and squeeze that into such a smaller amount of time was extremely challenging for a lot of forecasters. But this is good. We learned a lot by doing this work, and we can provide some guidance for how to analyze the data to try and avoid some of these peaks in workload during weather events. Okay, so that's one piece of the work. Another piece is an eye tracking experiment. A lot of the work that we do, we've done something called cognitive task analysis. And so we have forecasters work these simulations. We don't just want to know what the impact was on their warning performance, but we want to know why. What was it that you were seeing, thinking, and doing? And so in the past, we have collected hundreds and hundreds of pages of qualitative data. But as you can imagine, it takes a long time to go through and analyze those data. But not just that, it does depend on forecasters' abilities to retrospectively recall their thought processes accurately. I don't know about you, but sometimes I don't know what I did 5 minutes ago. And so there's definitely some limitations with that method. And so one thing that we decided to do was to integrate an eye tracking experiment into the work that we were doing. Eye tracking is an approach where we can try to objectively trace where somebody's attention is, and that can tell us about what is at the top of their cognitive activity, what is taking priority. Okay, so what we did on the computer here, what you can see is we have this simulation where we have our reflectivity data, we have velocity data, we have a control panel also, which is where they could issue warnings. And then along the bottom of that computer station, you can see an eye tracker. So it's kind of cool. It's remote. The forecaster doesn't have to wear anything. They just have to stay relatively still. And the eye tracker emits infrared light into their eyes, and they use something called dark pupil eye tracking. So essentially, they can track where the eye is located and corresponding to what is on the screen. And so we did this for a number of different experiments, but what I'm showing you here today is our pilot study. Before we did this, we didn't know of anybody that had worked with National Weather Service forecasters with this technology. So our first question was, what does the data even look like, and can it tell us anything new? Is this worth pursuing? So here's some results from this experiment. On the left, I'll describe this first. So we've got these 3 different pictures. The top one, so figure A on the top left, that's showing us the screen, so reflectivity data, velocity data, and then the controls along the bottom. Figure B on the left there is showing fixation counts. So the purples and the pinks are where the fixation count is highest. A fixation describes when somebody looks at a point on the screen for a certain amount of time. And when you fixate, that is information that you're extracting and processing. So we looked at the fixation count, and then we also looked at fixation duration. So when you do fixate on something, how long do you look for? And that's important because it can tell us about how difficult information is to process. So we have these heat maps on the left, but on the right, we also looked at temporal changes. So along the x-axis on both, we have 1 through 8, and that is a 5-minute period each time through the 40-minute period simulation. And then on the y-axis for A, we have the total fixation count, and then for B, we have the fixation duration. And the different colors represent different areas of interest. So reflectivity is orange, velocity is green, and then controls is blue. And what we were able to do when we looked at these temporal changes was see, okay, is there a signal that corresponds to that qualitative data where we know that there's something happening in the warning decision process that the eye tracker is able to capture? And we did see that. So if you look at period 7, so this is the first time that we saw the fixation count exceed that in the reflectivity for velocity. So this is the first time where the forecaster realized oh my gosh, it's been a hail threat this whole time. I've been focused on this area, but all of a sudden there's a wind threat and I'm concerned about a downburst. So in a nutshell, this approach was very interesting because we were able to objectively capture a change in the warning decision process. And that could help us try to summarize all of that qualitative data much more easier because it could point to interesting parts in the qualitative data. Okay, so we very much enjoyed working with this equipment, and we went on to do a bigger experiment that I don't have time to describe today. But this is a very interesting and eye-opening, didn't mean the pun there, but it was eye-opening to go through and do this research with forecasters. Okay, and so something else we do is focus groups. This is actually one of my favorite parts of the research process. This is the part where forecasters are really given a voice in the research process. Much of the time, they come to the Hazardous weather testbed and they participate in experiments and they're doing tasks that we've set for them. But at the end of the week, we oftentimes have focus groups, and this is where they can really tell us what they think. First of all, they can tell us what they think about the research study we had them participate in. We've been really excited to learn that sometimes they have experienced something that they can take back to their office now and make use of. But it also helps us identify areas where perhaps we could improve the research study to make it more appropriate for forecasters or perhaps enjoyable. So it's always a learning process. Also, these focus groups help to guide our future research ideas. A lot of the time, more so in the past, there was a focus on research to operations. But now we say research to operations and operations to research. Having their input guide what we are doing is just as important. And so that back and forth is something that we really appreciate. And then we also get a deeper insight into the operational considerations. I mentioned at the beginning of this presentation that we are always trying to promote this operational environment, but it's usually under experimental conditions. And so we don't have some of the constraints or the limitations that might exist in the real world. And so oftentimes forecasters can say, hey, have you thought about how this might work with, for example, staffing concerns or maybe fatigue because they work for a much longer day in the forecast office than during our experiments, or perhaps there might be technology constraints. And so they help us really map out what we need to think about if these things were to go into operations. Okay, so that rounds out a quick overview of some of the phased array radar research that we have done. I'm going to move on to talk about some of the work that I'm doing with weather model guidance. So this is quite different. What I'm showing you here now is 3 different panels. Okay, so we're looking at a different type of new information that forecasters might see. So we've moved from radar, now we're onto models. Okay, so on the left, this is showing a tornado watch. So this comes out of the Storm Prediction Center, and this tells you that tornadoes are possible in this location for a given time. This is issued many hours before the event actually occurs, and even before storms are even initiating and up in the sky. Okay, now on the right, you see a different image. This is tornado warnings. So we have a picture of the radar. Storms are ongoing. There are red polygons over a couple of those storms. That's where the tornado warnings are. That means that tornadoes are either imminent or they're occurring. Okay, so we have something that's issued many hours before. We have something that is issued hopefully minutes before. But we have this gap in time and in space. And there isn't a lot to provide forecasters with at the moment that provides them with additional guidance on individual thunderstorm prediction. But the National Severe Storms Lab have been developing something called the one-on-forecast system. This system is designed to produce forecasts for individual thunderstorms. And this means that hopefully we'll be able to provide a lot more specificity in where storms will occur and when before they actually are there. Okay, so from this model, what kind of information can we get? So before I go on to explain these panels, let me just mention that this model is an ensemble. So what that means is the model is run a number of different times. So we have actually 18 forecasts for the same event, but we just tweak them all a little bit so they're a little bit different. And what that does is it helps us take account of things like uncertainty in the observations that are being used to drive the model. And it helps us to better characterize the uncertainty that is inherent in atmospheric science. So we have this ensemble. So lots of different forecasts for the same event. And here is some of the information that we provide. Now, if you think back to your probability classes, some of this might ring a bell. On the left here, we have the probability or the likelihood of an event. So what we do is we set a threshold for something. And so this example here is focused on updraft helicity, which tells us about the rotation in a storm, but you could do this for wind, you could do it for hail. So for example, on the left, this could be showing what is the probability of exceeding 2 inches of hail, 2-inch diameter hail. And so where the reds are, that means that there were a lot of forecasts that exceeded that threshold. So they said, yes, there's going to be at least 2-inch hail here. Where the blues are, that means not many of the forecasts believe that would happen. So where there are areas of higher probability, that gives us greater confidence that, yes, this threshold is going to be met. In the middle, we have percentile products. And so this is different because what it does is it takes the numerous forecasts and it orders them in size from smallest to largest. And what it does is it allows us to look at a percentile. And so, for example, if we wanted to know, okay, we think that there might be hail with these storms, but if it does hail, what is the biggest hail that we could expect? Well, we could go and we could look at that distribution, that percentile distribution, and say, well, at the 90th percentile or the 100th even, so the top 2 forecasts, the biggest forecasts, what do they think is going to happen? And so between the left image and the middle image, we can ask, well, what's the likelihood of something happening? And if it does happen, how bad could it be? Okay, finally, on the right, this is paintball products. This is where we look at thresholds and with different colors representing different forecasts. It's kind of like a splat of paint. You look at different contours, and if they meet a certain threshold, you just plot it on the map. And so essentially what you want to see is if there are a lot of colors that overlay one another, that means there's a lot of agreement in the model or across the forecast for something happening there. If the paintballs or the contours are all over the place, then there's not much confidence, there's not much certainty. We say that that's a lot of spread, and sometimes that could be because the storms are quite difficult to predict that day. Okay, so this is a lot of information, and I know sometimes it can be hard to wrap your head around. But with that in mind, one of the jobs that I'm faced with doing is thinking about, well, how will forecasters use this information to improve the forecast process? So what you're seeing here is a couple of approaches that we're taking. On the left, we issued a survey to meteorologists, and we provided them with different images from the guidance to understand their interpretation. So do they understand what these images are showing them, and to find out, well, where are the challenges and the weaknesses in that understanding? And then indeed that has informed training that we can provide both to our operational forecasters as well as people that come and participate in our experiments. Okay, we've done a lot of work in the Hazardous Weather Testbed also for this weather model guidance work. This is a place where forecasters can build familiarity with the guidance and ask the people who are developing the model. They can ask them questions and build a good knowledge base of what's going on. But they also use the guidance to issue experimental products. And so what you see here are all these pink contours, and the pink contours represent different probabilities. So the likelihood of this area receiving some kind of severe thunderstorm threat for a given time period. And the hope is that these products will provide greater specificity or home in on the area where the thunderstorm is likely to produce a threat, more so than what the watch product currently provides. And then on the right, this is an image from some of the work I'm doing now, looking at forecasters' product usage. There's 26 different columns that go from left to right. These are different cases or different days when forecasters were using the website to issue experimental products. And with that, I was able to look at the type of products that forecasters prefer. So a different color represents a different forecast product type. And not just that, but I'm also looking at the order. So how do forecasters navigate through the model website and look at the different data? Because we have a lot of information, and a big question is, well, what do we need to include? And for the things that we do include, what is the most efficient and user-friendly way to present it to forecasters? So this type of work helps to inform those questions. Okay, we don't just work in the hazardous weather testbed. We also work with forecast officers who use this experimental guidance in real time to make real life decisions. And so these are some photos from the different work we're doing with forecasters. In the top left, this is where some of my colleagues and myself actually have been down in the Norman Forecast Office. It's super convenient since we're co-located to go and work with them, to shadow them and see how they are using the guidance in real time, but also to provide some real-time support in how to interpret the information that we're producing. The flash flood product issuance, that is for the Weather Prediction Center. They are a national center, like the Storm Prediction Center. They're based out in Maryland, and they focus on precipitation threats across the country. We've worked with those folks for a few years now to see how they will use our guidance to issue products. And then finally, we are working with a subset of offices in the southern region. So that's the pink outline there. We've got 9 different offices who we're working closely with to really build a good picture of how this guidance might be used in operations. Okay, before I wrap up, I did want to mention that there is other end user research going on at the National Severe Storms Lab and in the Hazardous Weather Testbed. There's a lot of great scientists doing all kinds of work. The Satellite Proving Ground is one experiment that's gone for many years. They're looking at how forecasters use the new satellite information during the forecast process. On the bottom there, that's a photo from the spring forecasting experiment. This experiment was actually really where the Hazardous Weather Testbed work originates from. It's been going for, I think, 20 years now. And they bring in folks from all across the country as well as from other countries. I think they have about 100 visitors a year who participate in their experiment. And then it's not just forecasters that we work with. There's a group that work with broadcast meteorologists, because the things that we're developing are going to impact the type of information they share with the public. But understanding the limitations of being on air and the TV world is a different world to the research world. And so understanding what it's like for them and how they could use this information is very important. And then finally, we have emergency managers who come to experiments, because these are the folks who are making decisions to protect your communities when weather is threatening it. And so they want to know what we're producing, and we want to know how they might use it. Okay, this is my final slide. A little bit of inspiration, I suppose. Moving forward, this is a collaborative effort. Lots of people working on lots of different projects. This is called Forecasting a Continuum of Environmental Threats, or facets. This is a forecast paradigm or framework that we are working towards, and we are trying to achieve. And this is where we will be able to have a more continuous flow of information. So you would get more updated information on severe thunderstorm threats and other weather threats more often, but also it would be probabilistic. And so at the moment, the system is very binary, yes, no, but meteorology is uncertain. There's no absolute yes, no knowledge that we can have before storms occur. And so integrating probabilistic information is really a natural way to go. And so with that, we have the physical sciences. These different icons represent different phases of the facets framework. I've talked mostly about the forecaster today, but the other areas are very important. And with the physical sciences, we integrate social, behavioral, and economic sciences also. And so that is my final slide. Thank you so much for listening, and I will hand it back to Leah now. Thank you.
Thank you, Katie. That was great.
Thank you.
Yeah, it was really, really interesting to hear about some of the higher level decisions that you might make when most of us at the lower level are seeing those decisions come out on the radio or on the television.
Yes, yes, there is a lot that happens behind the scenes, that's for sure.
So that kind of led me to a question to kick us off here. We live here up in the high Sierra Mountains, and of course, our severe weather comes in the form of winter storms, which can be tricky for road conditions and other things.
Mm-hmm.
So I wondered if you could talk a little bit about the responsibility of a weather forecaster in those conditions, and how a weather forecaster looking at a severe storm might understand which weather model to focus on.
Sure. So winter weather it's not an area I've specialized in, but certainly it's something that forecasters, all of the 122 different offices are responsible for providing information on. And so usually what you will see is things will come out of the National Center, the Weather Prediction Center, many days before winter weather is expected to occur. And what you will see on the TV usually comes, or from your local forecast office, that will come later than the work that the forecasters are doing beforehand. And so what you don't see is the forecasters will be working with city and state emergency managers. So if it's anticipated that this is going to be a big storm, they'll be providing webinars, briefings. There's a lot that goes on behind the scenes. A big focus for the Weather Service lately has been on the communication of how severe storms or winter storms might impact communities, so impact-based decision support services. That's something that has grown lately for the Weather Service community. A lot bigger focus right there. And so these things happen behind the scenes. And then in terms of the models that they use, there's a whole bunch of models that forecasters can look at. And they all have their strengths, they all have their limitations. And part of that might be geographical. So they know, okay, well, for this area of this country, we know that this model does really well. Or perhaps for this type of weather event, this model is going to better predict this hazard than this other model. And so forecasters, a lot of the time, it's built up through experience, through learning the strengths and limitations of models, understanding what their biases are. So for example, does this model tend to always over forecast snowfall? And so do I just calibrate myself and adjust my forecast? And so it really is about building experience over time and learning what it is that works well for specific scenarios.
Mm-hmm. Fascinating. It sounds like a very interesting job.
It is. I mean, the weather always changes as well. So the type of problems that you might be facing or forecasting, those change daily for forecasters. Yeah.
So we have a question here from a watcher, Laura. She says, due to climate change and global warming, hurricanes and other less deadly storms have become more severe. Why is this?
That's a great question, and that's a true observation. So good job, Laura. So a lot of the reason here is to do with the energy that the atmosphere can hold. With climate change, I'm sure everybody's familiar with knowing that the temperature is increasing. And so when the temperature increases, the atmosphere is able to hold a lot more moisture and therefore a lot more energy. And so we are seeing hurricanes that are more impactful. We're seeing, for example, think of Hurricane Harvey. That event produced an incredible amount of rainfall over the Houston area and surrounding areas. And then for severe thunderstorms, we do see that some of them are becoming more deadly, but also that they're shifting in location. So we're starting to see a shift towards the southeast, or perhaps not what we would typically think of as Tornado Alley. And so a lot of it is to do with the way in which the environment is changing and what it's capable of doing.
And then we have a follow-up question from her as well. Is there a reason why tornadoes are so hard to predict?
There's a lot of reason. In the meteorological community, I think since Doppler radar became a capability in terms of observing storms, that's where we can look at storm motion. Once we had Doppler radar, which was in the 1980s, and then 1990s was when it was really installed across the United States. That was when we could first start frequently observing the motion in storms. So being able to see, okay, well, what are the dynamics at play? And so things like looking at mid-level rotation and seeing how it tightens and descends through the storm, or other studies have found that rotation actually starts at the ground and then evolves upwards towards the storm. So these phenomena are extremely hard to predict because our understanding of thunderstorms is certainly not complete. Our ability to observe all of the processes is still limited. So the example actually is perfect with phased array radar. We saw temporal resolution increase quite drastically. And with that, we were able to better see trends in thunderstorms. So, okay, I see from minute to minute that this rotation is descending in this way, for example. But before that technology, we weren't able to observe those trends. So part of it is our understanding, we're still learning. Our observations, we're still limited in some ways what we're able to see in the thunderstorm. And these phenomena, they're so dependent on a huge array of variables that are thermodynamic, that are dynamic, and being able to pinpoint specifically why a tornado occurs is really tough. But there's lots to learn, so it's a great time to be part of the field.
Fascinating. So going back to the weather radar, the first experiment you were talking about, you talked a little bit about the eye fixation and studying what specifically forecasters were interested in looking at.
Mm-hmm.
So what were some of the specific components of the data that you found people were looking the most at?
Right. So for our experiment, we focused on just reflectivity and velocity data. A, to keep it quite simple, and B, the phased array radar, because it's experimental. Those are the main products that we can focus on. And so what we saw was, one of the things that we did was we tried to look at scanning patterns. So not just how often do you look in this area of interest or that area of interest, but how do you move between different points on the screen? And so it was interesting because we saw that scanning patterns actually were incredibly different for some forecasters. So you might think, you've had the same training and you're using the same observations, and so maybe you analyze data in the same way, but actually we found that it was incredibly different. And that was an interesting finding because that can inform us on things like training. If we're seeing that it's so different, how does that relate to performance, for example? So that's one thing that was interesting, just how different it was among forecasters. What was interesting that I didn't expect to see was the eye tracking data helped detect instances when forecasters were having technological challenges with the interface. And, you would see quite sporadic eye movements. And then when you go back at the video and you look, it's because things weren't behaving like they were supposed to on the interface. And so that's actually useful for being able to do software development and improvement, or just pinpointing what was going on. We weren't one of the things that we tried to do in our bigger project was to see if there was uniform difference in eye movement patterns for people that were using fast and slow updates. That wasn't something that we saw in the one experiment we did. That's something that I was hoping to see, but there were just so many differences within forecasters themselves. It was hard to pinpoint.
Very interesting. Sounds like a project that has a lot of research possibilities.
Oh my gosh, yes. I haven't done eye tracking research since, but there are 100 questions just from that study alone lingering. So who knows? Who knows if we'll go back down that path?
That's great. So we actually have a comment and a question here that I think we're going to wrap up with. Lara again says, thank you. And are there any additional resources to learn more about what you've talked about today?
Yes. So The National Severe Storms Lab has its own webpage. It's actually a wonderful resource. It describes all the different projects that are going on at the lab, and they have something called bite-sized science videos. And so those videos, in a very, I think, clear and nice format, describe the different projects that are going on at the lab. One of those is focused on the eye tracking experiment I did, but there are a lot of other great videos that describe other projects, some of them that are happening in the hazardous weather testbed. So I would start there, and there's a lot of links to other resources from that webpage. So that's for the National Severe Storms Lab.
Great. Well, we just want to say thank you to Dr. Katie Wilson for presenting your research and for donating your time today to do this talk. It was great. Thank you so much.
Great. Thank you. I had fun. Thank you very much.
All right. We'll talk to you next time.
All right. Bye-bye.
Bye.